Okay, so this is a quick sound test. It probably still does chop the sound. I'm not yet quite sure why. This audio interface should be fine. Shouldn't be the interface. Shouldn't be the preamp. Could be the connection. I'll give it another go today. I'll see what the issue is. I hope it's not too bad though, and you guys are able to follow. Let's give this a quick check. Okay, so it seems sound is coming through. All right, let's start. So algorithms and data structures, right? I'm gonna go with by a couple of different books because they all have their use cases. This is the Bible of it all. Introduction to Algorithms. The problem with this book is it's a reference. It is not a textbook. It is not a tutorial. It does go over how to think about designing algorithms from scratch, but this is not what the book is for. The book is more of a reference. When you have a problem at hand, you think, oh, I need a red black tree, for example, and I forgot something about their implementation. You pull this book, you open red black trees, and there you go. Everything about it, and its asymptotic runtime and how to implement it, etc. So it's a fantastic reference. Uh, not so great in my personal opinion as a textbook. There's a book by Sciana. Uh, let's take a look here. What was it called? I don't want to say the wrong thing here. And Algorithms Design Manual. There it is. The Algorithm Design Manual by Steven Sciana. I actually like this book a lot more, for just learning how to think about algorithms. What he does is he has these things called war stories, which are real scenarios from his own personal experience of various companies or clients asking him to design certain software and how he approached the algorithmic problem, how he uh, sort of posed the problem mathematically, algorithmically, and then how he went about it, how he went about the problem. The thing about world problems is that they're usually, you can't just pull a cookbook algorithm and apply it to the problem. You still need to play around a bit and think about how to modify things here and there. Nevertheless, we'll start here. It's a good start. So we're gonna go in order from the first chapter, and the book is enormous. So obviously, we're not gonna go line by line. A lot of lines. We're gonna skip to the crux of it all, essentially. So we start chapter one. Or chapter one. Let's see. Okay, foundations. Chapter one. Let's see what the foundations are here. So they go about defining what an algorithm is, and I won't define it. I won't give the exact definition. You can read the book for it yourself. But intuitively, what an algorithm is it's sort of like a recipe, right? It's a set of steps that you perform to reach from some kind of an input to your output. It's the recipe. It's the steps your computation performs. So, for example, if you have a sorting problem, and you first thing you want to do is you want to formalize your problem. You want to really understand what is it I'm trying to solve, what are my inputs and what are my outputs. So in a sorting problem, you have a sequence of n numbers, right? Here's this vector from A1, A2, all the way to AN, any numbers, right? And what you're looking for is a permutation of the sequence such that these numbers are in monotonically increasing order. And that's the definition of the sorting problem. Okay. So now that you've defined your problem, you can go about solving this. And they give an example here. Here's a vector of numbers, and here's the output after they've applied some kind of a sorting procedure. Okay, such an input sequence is called an instance of the sorting problem. In general, an instance of a problem consists of the input needed to compute a solution to the problem. Okay, so this is kind of important because it's important to realize that just because we ordered this specific sequence of numbers doesn't necessarily mean that our procedure is correct in general. Okay? It means that our procedure works for this specific sequence, but if we were given a different sequence, whatever our procedure is, it might have broken. Okay? It might not have worked. So an algorithm is correct if it works in all cases of our problem definition. So here's our problem definition for any such sequence, whatever our procedure is, it needs to provide this correct output. Then we say our algorithm is correct. Okay, so moving on, what kinds of problems are solved by algorithms? So this is something I've personally worked on. This is the Human Genome Project. And we're identifying genes in the human DNA. So today we're identifying many, many more than this. And the issue is you're dealing with entries. You can think about these sequences as, it's just they're enormous, right? They're like about 3 billion, more than that. And whatever operations you decide to do on these sequences, if your procedure is computationally slow, you will notice it. It'll take you a long time before any of these computations on this DNA readings get completed. So you want a procedure that is quick, precise, correct. So algorithms become very important in this problem. What else do I want to say? The thing about algorithms in general is that if, for example, if you know that your input is always going to be 5 numbers, you're going to have a list of 5 numbers. You might not care, right, what you're sorting. It could be the bubble sort for all you care. For 5 numbers, it doesn't really matter. Computers today are so fast that you won't notice a difference at all. So algorithms come into play when your input scales, right? When you're working at scale, your input's huge, then you start noticing these things. All right, here's another problem. We're given 2 ordered sequences of symbols, X and Y, notice ordered, and we wish to find the longest common subsequence. So at some point, if we start at some point, we will have a subsequence, right? And we want to find the point where we have the longest one. A subsequence of X is just X with some of its elements removed. Okay, so if you take X and you keep any set of its elements, you have a subsequence of X, right? For example, one subsequence of A, B, C, D, E, F, G is just B, C, E, G, B, C, E, G. So these are the way they define a subsequence is they just keep some elements from the original sequence in their original order. So the length of the longest common subsequence of X and Y gives one measure of how similar these two sequences are. Okay, so mathematically speaking, there are many measures of similarity between two sequences, right? There are things called cosine distances between sequences, between vectors and whatnot. Here, the way they define distance between two sequences is the length of the longest common subsequence. Okay, so that's another procedure, right? What do we have to do? I mean, potentially we might have to go deep into both X and Y before we find that longest sequence. We might even have to go through all of them, right? I mean, imagine how many steps that would take, especially if your M, if the size of X and the size of N are size of Y are large, that's going to take a long time. So how much time? Here they specify if X has M symbols and Y has N symbols, then X and Y have 2 to the power M and 2 to the power N possible subsequences. Why is that? Where are those numbers coming from? Let's do a quick analysis here. Well, suppose I have a sequence. Here are my values. X, let's say I have a vector. Now, I come from math, so I apologize in advance, but I write my vectors as columns. Okay, so suppose we have what A, whatever C, D, F, blah blah blah. Okay, this is some some vector, and these are, let's assume these are some numbers, whatever. We're pulling from some field and dimensional field. Okay, some vector field, right? Vector space. Here's a concrete example. Okay, so let's do 1, 2, 3, 4, 5, and 6. There we go. Now I tell you, form a subsequence for me from these elements. Okay, well, now you have choices. You have a lot of choices. You could say this. You can say, I can keep the one or I cannot keep the one, right? I have 2 choices for this element 1. And suppose you want to keep it. There you go. Next, you say, I have 2 choices for the number 2. I can keep it or I cannot keep it. Suppose you choose not to keep it. Okay, you don't keep it. You go to 3. I keep it. 3. You go to 4. I don't keep it. You go to 5. Keep it. 6. Don't keep it. There you go. I have a subsequence. So again, what do we have? Here's our number 1, right? We have 2 choices. Keep, don't keep. Okay. Now, if we keep 1, right? This is keeping 1. Then we go, and this is not keeping 1. We go to number 2 here. Now we again have 2 choices. Keep 2 or don't keep 2. Here as well. Keep 2, don't keep 2. And let me just draw this state of the tree in terms of subsequences so you see each one of these paths. Each one of these paths in my tree results in a subsequence. This first path, K1, K2, what does that give me? Well, I kept 1 and I kept 2, right? And this should be don't keep 2, don't keep 2. Okay, this first sequence, this first path, K1, K2, says keep 1, keep 2. This one, K1 and 2, says keep 1, don't keep 2. Don't keep 2. It's just the 1. This one, N1, K2, says don't keep the 1, but keep the 2. And finally, this one says don't keep the 1, don't keep the 2, so it's just empty. We don't have a sequence, right? It's the empty set here. And then for number 3, we have the same thing. Keep 3, don't keep 3. Don't keep 3. And you see that this tree is a binary tree, right? It's a binary tree. At each step, we split in 2. We either keep or we don't keep. So 2 choices for number 1 times 2 choices for number 2 times 2 choices for number 3, blah, blah, blah. However many numbers we have. In this case, we have 6 of them. And so in total, we'll have 2 to the 6th power choices, right? That's how many subsequences we can form, 2 to the 6th power. In general, if we have n numbers, not 6, the answer will be to the nth power. And that's where they get the answer from, 2 to the m and 2 to the n. So selecting all possible subsequences of x and y and matching them up could take a prohibitively long time unless m and n are very small, right? This makes sense because look, these are exponential, base 2 exponentials. If m and n are both large, this will not stop, okay? I don't care what your machine is, unless you're running quantum computation, this thing might never stop. Well, theoretically, practically, not theoretically. So you need algorithms. You need a better method of finding the longest substring. This just doesn't cut it. Okay, moving on. Let's see. So when you talk about algorithms, when you're making a procedure that can do computation quickly, oftentimes part of this process is the idea of storing your data efficiently. Suppose your algorithm requires to pull data from some place, right, several times. Read this data, manipulate this data, blah, 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 right? And suppose if you're manipulating this data somehow after you read it, that manipulation itself is an expensive procedure. So you tell yourself, okay, what if I could manipulate the data once, store it efficiently, and then be able to pull that stored result whenever I need it? So the way we store the data for efficient use it relies on the idea of data structures. Okay, these are structures that help us store data efficiently. So data structure is a way to store and organize data in order to facilitate access and modifications. Okay, and this is important. No single data structure works well for all purposes. We know like hash maps are sort of the go-to data structure, right? And they're so good, but even those guys are just not the best in all cases. Oftentimes you have to think, which data structure should I use? If you don't know what data structure is, don't worry about it. We'll get there. It's hard problems. So hard problems. There's a class of problems called NP complete. Let's give this part a quick read here. So NP complete problems are hard, and by hard, what do I mean? I mean this. It has no known efficient algorithm. Okay, there is no known efficient way of solving NP-complete problems. There's a very famous algorithm like that called the traveling salesman problem. We'll take a look at that in a second. And it is NP-complete. Okay, now how do you prove that a problem is NP-complete? Well beyond the scope of what we're talking about here. But just know that there's a class of problems called NP-complete. Parallelism is, we can oftentimes take an algorithm, and today's machines are able to execute instructions in parallel. Okay, not sequentially, not, they don't have to wait for one instruction to finish so they can execute the other one. They can perform operations simultaneously. I'll give you an example. So GPU programming is fantastic for this. And here's what GPU programming can do for you. Suppose I want to add two vectors, right? So I want to add 1, 2 to 3 and 4. So if I'm writing some kind of a loop that adds the entries in each index to each other, so 1 plus 3 would give me 4, right? Then my loop would go to the next index, and 2 plus 4 would give me 6, and I'd be done. This is a sequential process. We did the first index first, then we did the second index, okay? What we can do is we can do this in parallel. So we can say the 1 plus 3 step is completely independent of the 2 plus 4 step. There's no dependency. The 2 plus 4 does not need to wait for the result of 1 plus 3. So when this is the case, when these steps, these arithmetic steps, are completely independent of each other, that's your cue that you should look for a parallel solution. Okay. And then what will happen is somewhere over here, the computer will do 1 plus 3. It'll get its result, right? It'll get its 4. Somewhere else, it'll do 2 plus 4. It'll get its result, 6. And then these two results will come back into this single vector. Okay? There won't be a wait time. This is not a sequential process. This is a parallel process. How do you write parallel algorithms? A little more complicated. Hopefully, maybe. We'll get into that later. So they say it's chapter 27. Okay. So some exercises here. These are very sort of general questions. For example, select a data structure that you've seen previously and discuss its strength and limitations. So a very common data structure that most people have seen are arrays, right? I mean, if you've worked in C or you're coming from some low-level language, you've seen arrays, lists maybe in Python if you're from there. All it is just a container of continuous memory, right? So, and in this memory, let's say we have containers, container of integers. We can have like 1, 2, 3, -1, 4, for example. And in memory, these are laid out next to each other. Now, here's an array. What are its strength? Its strength is that because in memory, it's laid out, they're packed, they're laid out right next to each other. If I know the memory, if I know the address of this memory location, right? Let's say its address is 4. Let's just say there's some address number 4. If I know this address and I know the size of an integer, I know the size of an integer in bytes, then all I have to do is to access this number 3 here, I can say go to this address 4, and then go, let's suppose integers are 4 bytes, right? Then go 4 bytes over, and go 4 bytes over more. In total, how many was that? That was 8 bytes, right? We went 4. That's 8 bytes. So I could have said go to that address and just immediately jump 8 bytes over. And we're immediately here at the entry that we want. I want this one, this -1. Instead of 8, I do 12, right? 4 more bytes, 12. So I say go to this address, go to the start of my block of memory, and just jump over 12 bytes. And now we have this entry immediately. So it's what's called random access, right? It has very fast random access. We can pull any one of these entries instantly. What is its limitation? Its limitation is fixed size. When you declare an array, you declare some chunk in memory. Okay, your operating system gives you that memory. It's a fixed size. Okay, this is fixed size. So if you want to add something else to this list, if you want to add another number, what has to happen is you have to tell your memory, hey, give me another list that is large enough to contain one more integer. And so your operating system will now make another one of these chunks of memory, and then you have to copy all the entries that you had previously, copy them over, and then new one you want to insert, you can now insert here at the end. So insertion of a new element is problematic, and that's a drawback. Okay, so I encourage you to look through these. How are shortest path and traveling salesman problems given above similar? How are they different? Okay, so traveling salesman problem, what does it say? Let's take a look. So let's traveling salesman problem, Wikipedia. Let's see what that even is. Traveling salesman problem asks the following question. Given a list of cities, okay, and in this picture here, each red dot would be a city, and the distances between each pair of the cities, what is the shortest possible route that visits each city exactly once and returns to the origin city? So for example, let me see if I can, yes, there we go. For example, if we start at any one of these nodes, suppose we start at this leftmost middle node here. The question says, what is the shortest possible path I could take that would get me through all of these nodes, all the cities, and come and bring me back to my point of origin? Okay, that's the question. So you can imagine if you're a mailman, for example, this might be a good thing to know, right? You want to minimize the time you're en route, or you want to minimize the total distance you travel. So the question says, what is the shortest possible route? You want to visit some routes to drop off mail, but you want to do that in the shortest possible. You want to cover the shortest possible distance, right? You don't want to waste gas, for example. And this is an NP-hard problem, which means what? Which means that we don't have a general efficient algorithm for it. Okay. Shortest path problem is a bit different in a sense that in a shortest path problem, I don't require you to come back to the point of origin. I pick a point, I pick a node here, I pick a node here, and I say, find the route from this node to this node that is the shortest. Okay, and you can imagine these lines that connect them. Let's just say this. Let's say if the longer the line is, the further those two nodes are. Okay, so the length of the line is the distance. So I might say you start here at the left middle node, you end at the right top node here. Find me the shortest path between them. Traveling salesman problem requires you to come back to the node of origin, and that turns out to cause all kinds of havoc. All right, algorithms as technology, efficiency. Okay, let's talk about efficiency here. So what is efficiency of your algorithm? Now, let's do an example here. So suppose I tell you to do the following. Suppose I give you some numbers, 3, 4, 0, 5, -1, 6. And I tell you to sort them. Give me a procedure, some algorithm that will sort these things. So you tell me this. You tell me, okay, here's what I'm going to do. Okay, I'm going to start from the very first number, and I'm going to keep cycling through these. I'm going to keep looking at each number, and I'm going to find the smallest one. And I'm going to replace this first number with that smallest one that I find. I'm going to swap them, in essence. Okay, let's do that first step. Well, the smallest one here is the -1. It comes here. Everything else stays the same. The 3 is now over there. There we go. Okay, now we do the same procedure on this part of the list. I don't care about the very first element because I already know it's the smallest because I had looked at my whole list. This is the smallest and it is in its correct position now. It's in the first position. So that is fine. I don't need to look at that anymore. I look at this guy now. I do the same thing. I go through these elements. I pick the smallest one and now I'm going to swap it with this 4. Well, which one's the smallest one? It's the 0, right? So after the second step, I have negative 1, 0, 4, 5, 3, 6. Now I no longer need to look at these two numbers. They are already in their correct positions. They're sorted. So now I do the same procedure on these two, on these three. I'm sorry, these four numbers. And now you can imagine that after we do this procedure, several times, we'll end up with a completely sorted list, right? We'll end up with negative 1, 0, 3, 4, 5, 6. Now, the question is, how many steps did we perform? Approximately. Okay, I'm not going to ask you to count exactly the number of steps, the number of comparisons, the number of swaps, etc. I mean, if you're into this stuff, it's a good idea to do it. And if you like that kind of thing, I strongly recommend Knuth's books. However, we're not going to do that kind of thing. We're just going to approximate. How many steps did we take? Let's see. So in my first step, I had to look at all of the entries, right, to pick out the smallest one. How many entries did I have? Well, in this example, I have 6 of them, but let's generalize this. Suppose I have n entries. So in the first step, I look at n entries. Pick the smallest one, put it up front. We go to step 2. How many entries do I look at now? Well, I no longer look at the first position, right? So I'm looking at n minus 1 entries now. So I do n minus 1 steps. I go to the next iteration. I don't look at the first 2 elements now. I look at the others. That's n minus 2 elements, right? We had n total. We don't look at 2 of them. So that's n minus 2 elements. Now you can imagine on the next step, you'll be looking at n minus 3 elements and all the way down until you're just left with a single element. Okay, you'll be going down all the way. And if you look at this, if you look at the sum, this should be familiar to you, right? This is, of course, n times n plus 1 over 2. Okay, so this is n squared plus n over 2. And now you look at this, and if you've taken any calculus, you can say this. You say, okay, let's just imagine that n becomes huge. The number of entries, like imagine this is coming from the human genome readings, the DNA readings. There are enormous number of these things. So you can say, okay, let me just take the limit as n. Let me take the limit here as n goes to infinity of this, and you can see that your algorithm just explodes because, of course, this limit is infinity. And this makes sense, right? I mean, the more things you have, the more, the larger amount of steps it'll take. So in the limit, if you have infinitely many terms here, your algorithm will not end. But when n gets really large, which term is dominating here? Is n important? Like when n is a trillion, for example, n squared is much, much larger than n. So if you've taken limits, if you've done calculus, you essentially know that you can ignore the n, you can ignore the constant factor here, and so you can just keep the n squared. And this procedure of this procedure of keeping the most important, this most dominant term in this expression, we signify. So that's what we're going to do. We're going to keep the most dominant term. Later on, we'll introduce some notation for this. We'll call it the big O notation. But the essence is that you have the expression, relatively speaking, the exact expression of how many steps you have. Then you imagine that the size of your problem gets big. You have a lot of inputs. And now, out of this expression, you say which term dominates. are there any terms that I can toss? Well, I can toss the constant factor, I can toss the linear term, and I'm left with my quadratic term. Quadratic, n squared. So this algorithm is quadratic. This sorting algorithm is quadratic in the size of the list of entries. Okay, so that's one measure of efficiency. Okay, this is the time measure, how many steps it will take you. Another measure of efficiency that you can think of could be, for example, space efficiency. As we go through our algorithm, is there any extra information that we need to store on the side in our computer, in the memory of our computer? Maybe, for example, we need to store maybe we need to store a bunch of different numbers in memory in a new list, and this new list keeps growing, right? So you can imagine that the space, your algorithm might be efficient in time. It might take few steps, but not efficient in space. It might take a ton of memory. So there is this, we'll see that there is this trade-off between time and space. Do I want an algorithm that's very fast but takes up a ton of space in memory? Or do I want an algorithm that is not the fastest but takes much less memory? Now, again, depending on your data sizes, if you're working with the gene sequences, you will definitely be worried about space. But in general, with the amount of RAM that exists in PCs today, time is the one you worry about the most, honestly. All right. Now, let's keep scrolling. Let's look at this exercise 1.22. Suppose we are comparing implementations of insertion sort and merge sort. These are two sorting algorithms. We don't know them, suppose. So for inputs of size n, they tell us that insertion sort takes this many steps, 8 times n squared, while merge sort takes 64 times n log n steps. For which values of n does insertion sort beat merge sort? So for which values of n, what is n? N is the size of our input, how many numbers you have, right, in the list. So for which n is 8n squared better than 64n log n? Okay, so does insertion sort beat merge sort? So here's what the question essentially boils down to. They're saying the following. They're saying if insertion sort, let's write that here, insertion sort, which has a time complexity of 8n squared, right? This is the number of steps when your input has size n. Then you have merge sort, and this one is 64 times n log base 2 of n. And they're saying for what n is this expression larger than this expression? That's essentially what we're interested in, right? The question, when does insertion sort beat merge sort, boils down to when are this number of steps less than, not greater than, less than this number of steps. We want this algorithm to finish faster than this one would. The way that would happen is that if the number of steps is less than the number of steps of the merge sort. So we want to know for what n are these many steps less than these many steps. Now we have a simple inequality. We can solve this. Well, we can assume n is not 0. It would make no sense if you just have nothing to sort. So that we can divide both sides by n, right? And n is positive. Because why is it positive? Because n is the number of items. It's a natural number. So we know that our sign is not going to flip. We have 8n less than 64 log n. Let's divide both sides by 8 as well. So we have n less than 8 log n. So this is our question, right? N less than 8 log n. And this is base 2, of course. That's what log is. LG is base 2. And if you want to try and solve this inequality, I leave this up to you. I strongly encourage you to try and solve it yourself, but you don't have to go far to realize when this stops working, right? So look, if n is 1, let's try and plug in. N is 1. Is 1 less than 8 times log base 2 of 1? Log base 2 of 1. So is it less than that? Then go to 2. Say, is 2 less than 8 times log base 2 of 2? What about 3? Is 3 less than 8 times log base 2 of 3? Right? Is 4 less than 8 times log base 2 of 4? So do this procedure and see if you can come up with an n. It won't take you a long time, I promise. It won't take you very long. You will hit a limit. You'll come up with an n such that after that point, n becomes larger than this expression. Okay, and then you know that after that point, merge sort becomes a better algorithm than insertion sort. Okay, so that's one way to approach this problem. So all we're doing is we're saying if we don't know how to solve this inequality analytically, we're just going to plug in numbers. Now the thing is that we can. This n is not a real number; it's a natural number. So we can actually plug in these values, and we know that we're covering all the cases. We're not missing any cases. These positive integers are all the cases for n. N is a natural number here, and it won't take us very long until we find what this n is. Okay. And it's the same kind of question here. It says, for what is the smallest value of n such that the algorithm whose running time is 100n squared runs faster than the algorithm whose running time is 2 to the n? So what is the mathematical inequality they're asking us to solve? They want us to do this. They're saying, let's go back to the question. 100n squared runs faster than 2 to the n. So here is our inequality. 100n squared should be running faster than 2 to the n. Okay. Now again, you can do some kind of approximations here. If you can't solve this analytically, you can use a computer. You can plug values of n in. And again, this won't take very long. This is exponential. This is an exponential. This is a parabola. It's quadratic. This thing just shoots up. It will completely overtake this parabola very, very early on. So if you want, you can even start plugging in natural numbers and you'll see what n should be. Okay. So comparisons of runtimes. Now, for each function fn and time t in the following table, determine the largest size of n for a problem that can be solved in time t, assuming that the algorithm to solve the problem takes f of n microseconds. So where is our fn? Here is our fn. On this first column, these are our functions. What are we asked to do here? We have our functions, our runtimes. And what do we need to do? Determine the largest size, n, such that our runtime takes 1 second. Okay? 1 second. So for example, if you let's pick log n. Let's pick the first one, log n here. So our fn is log n. This is our time. This is in microseconds. What does that mean? That means if I plug in a list that has 3 things, I have f of 3 equals log 3, log base 2. This is LG's base 2. So log base 2 of 3, and this is the number of microseconds it's going to take me to finish the problem. Now, I want to finish the problem within a second. Now, you say, okay, let's say you don't know the metric system. You say, how many microseconds in a second? So how many microseconds in a second this many. Okay? So we have 1,000,000 microseconds in a second. 1,000,000. You go back to your problem. You say, okay, so the question that this boils down to is, what should n be so that this number is less than 1,000,000? Because the unit of this is microseconds. We want the total runtime to be less than less than or equal to a second. A second is 1,000,000 microseconds. So this needs to be less than or equal to 1,000,000. So log, we'll call this n star, whatever that n is, should be less than or equal to 1,000,000. And of course, we know how to solve this. We can exponentiate both sides, right? E to the log n star less than or equal to, or 2, excuse me, this is base 2. 2 to the 1,000,000. And of course, on the left side, we're just left with n star, 2 to the 1,000,000. So that is enormous. Okay, that is absolutely enormous. If it takes me that many microseconds. So if n is 2 to the 1,000,000, then I will fit within my desired runtime here. So again, what was the process? The problem says we have log n, and we can assume, for the sake of this problem, assume that the algorithm to solve a problem takes f of n microseconds. To solve a problem takes this many microseconds. I want to fit in a second. So how many microseconds are in a second? 1,000,000. We went back, we set up our inequality. We said if we take this many microseconds, I want this many microseconds to be less than or equal to 1,000,000 microseconds. And then I wanted, of course, to solve for n. I wanted to find what n was. So I exponentiated both sides, and I got my answer. Okay, and this number, of course, is absolutely enormous. And what does this tell you? This tells you that logarithmic algorithms are good. Log n algorithm is fantastic. That's what you want. Okay. Now, if you go to the exponential algorithm, 2 to the n, and you say, what should n be? So it takes me 1 second to run. Okay, 1 second. Hey, let's even do 60 seconds. Okay, 1 minute. Let's do 60 seconds. Just so you see the contrast. Let's go down. We have an algorithm that runs into the answer. Our function is 2 to the power n. We have an exponential function. And now it's the same question. We say, what should n be so that 2 to the n is less than or equal to 60 seconds? Now remember, the unit of this we assumed was microseconds. Microseconds. Okay. So 60 seconds would be what? 60 times 1,000,000, right? 60 million. Now, if you want to know what n is, what do you have to do to solve this? Well, you have to take the base 2 log, right? Base 2 log. So n will be less than or equal to log base 2 of this number. Now, I'll leave it up to you to check that the log base 2 of that number is much, much, much smaller than this. Much smaller. So if I wanted to run within a second with the log n algorithm, I could have a much, much larger list than if I wanted to fit within 1 minute with with an exponential algorithm. So that gives you contrast between the log n and the exponential, that the log n is much better than the exponential. Your runtime is much faster. Now, here the functions are in increasing order. So the runtime is increasing as we go down. And I will leave it up to you to do this same procedure that I just did and fill in these tables. Again, you don't have to go and fill in all of this, obviously, If you already know how to code, maybe you want to run a little program that'll do it. If you don't, just I say maybe like fill in random entries from each row. Okay, from random entries from each row, pick like 2 columns randomly, 2 columns randomly for each row and fill it in. Okay, so there's a stark difference between log n and 2 to the n. Okay, moving on. So getting started, chapter 2. I will actually stop here since it's already 3:55, and I will actually move to chapter 2 next week, the official week when things kick off. This is still the test week. Now, hopefully this made sense, what I just did. This is microseconds, this is a second, etc. And you find n via simple solution, solving a very simple inequality. Work on this, and if you guys go through this table here, everything will become very clear, and you'll realize why algorithms are so important. As you just saw, the problem size, if I have an exponential algorithm, has to be much smaller than the problem size with a log n algorithm for it to finish in any amount of reasonable time. So go through this. If you have any questions, do post them in the Discord channel. Next time we'll get started. Let's see, with insertion sort. There we go. We'll get started with our first concrete algorithm, insertion sort, and we'll code it up in Python to quickly just throw it together, and then we'll do it in C++ or C. I'll be coding in C because I just like C, and yeah, and we'll pick up there. I'll see you guys next time. And I also ask you, if you're watching or listening to this, and if you're on the Discord channel, any comments or critiques or suggestions that you have, do write those, because I've never streamed things before. This is my first time. Obviously things are not perfect, but they will improve. But the only way for them to improve is if I get feedback from you guys. So definitely do post your suggestions. I appreciate it, and I'll see you guys next time.